Imagine a cosmic behemoth 10 billion times the Sun's mass siphoning gas from a nearby star, its event horizon glowing like a black hole devouring light itself. This isn't just any black hole, it's a supermassive monster in a distant galaxy, 12 billion light-years away, its hunger captured in stunning detail by NASA's James Webb Space Telescope. The image shows a swirling accretion disk, heated to millions of degrees, radiating energy so intense it outshines entire galaxies. But here's the mind-blowing part. The black hole isn't just feasting, it's launching twin jets of plasma at near-light speed, carving pathways through interstellar space. These jets, visible in infrared, reveal the violent dance between gravity and radiation, a cosmic ballet of destruction and light. Webb's infrared eyes pierce through cosmic dust to witness this rare spectacle, offering a glimpse into the engines that fuel the universe's largest structures. This isn't just a black hole eating, this is a universe-scale feast, and we're finally seeing it unfold. In the vast expanse of the universe, where galaxies swirl and stars ignite, there exists a hidden engine of cosmic power, supermassive black holes. These titanic entities, millions or even billions of times more massive than our Sun, reside at the centers of most galaxies, including our own. For decades, scientists have studied these enigmatic objects, probing their influence on star formation, galaxy evolution, and the fabric of spacetime itself. But until recently, one fundamental question remained elusive: how do these colossal black holes actually grow? Now, a groundbreaking discovery by NASA's James Webb Space Telescope has shed new light on this mystery, revealing a supermassive black hole in the act of feeding, absorbing matter from its surroundings in a dazzling display of cosmic forces. This observation, made possible by Webb's unprecedented sensitivity and resolution, has provided astronomers with their most detailed glimpse yet into the violent, luminous processes that fuel these cosmic behemoths. To understand the significance of this discovery, we must first grasp the nature of supermassive black holes. These objects, with masses ranging from millions to billions of solar masses, are not merely collapsed stars but gravitational monsters that warp spacetime around them. Their immense gravity pulls in nearby gas, dust, and even stars, creating a swirling disk of material known as an accretion disk. As this material spirals inward, it heats up to extreme temperatures, emitting vast amounts of radiation across the electromagnetic spectrum. This process, called accretion, is the primary way supermassive black holes grow, yet observing it in detail has been a major challenge. The material around a black hole is often obscured by surrounding gas and dust, and the immense distances to these objects make it difficult to capture their luminous features with clarity. Until now, most observations of black hole feeding have been indirect, relying on the light emitted by the accretion disk or the powerful jets of high-energy particles that sometimes erupt from the black hole's poles. The James Webb Space Telescope, launched in 2021, has revolutionized our ability to study these distant phenomena. With its advanced infrared instruments and massive mirror, Webb can peer through cosmic dust and detect light from objects that are billions of light-years away. This capability has allowed astronomers to observe the accretion disks of supermassive black holes in greater detail than ever before. The recent discovery of a black hole feeding, specifically, the observation of its accretion disk and the glowing material surrounding it, represents a major breakthrough. By analyzing the light emitted from this disk, scientists can infer the black hole's mass, spin, and the dynamics of the material orbiting it. These insights are crucial for understanding how supermassive black holes evolve over time and how their growth influences the galaxies they inhabit. The black hole in question, located in a distant galaxy, is part of a rare class of objects known as quasars. Quasars are among the most luminous objects in the universe, powered by the intense energy released as matter falls into the central black hole. However, the specific details of this particular quasar's accretion process have remained elusive until Webb's observations. What makes this discovery remarkable is the level of detail captured. The telescope's instruments have allowed astronomers to resolve the structure of the accretion disk, revealing how the material is distributed and how it interacts with the black hole's gravitational field. This level of clarity is unprecedented, offering a window into the extreme physics at play in these cosmic engines. The data suggests that the black hole is actively consuming gas and dust, with the material forming a luminous, swirling disk that emits light across a wide range of wavelengths. This light, however, is not uniform. It exhibits variations in brightness and color, hinting at the complex dynamics of the accretion process. One of the most striking features observed is the presence of a glowing halo of material surrounding the black hole. This halo, likely composed of ionized gas, is thought to be the result of the black hole's intense gravitational pull and the extreme temperatures generated by the accretion disk. The gas in this halo is heated to millions of degrees, causing it to emit light that can be detected by Webb-sensitive instruments. This halo provides critical clues about the environment around the black hole, including the density of the surrounding material and the rate at which the black hole is accreting mass. Additionally, the observations have revealed the presence of high-energy jets, streams of plasma propelled at nearly the speed of light emanating from the black hole's poles. These jets are a common feature of active galactic nuclei, but their exact mechanisms and role in the black hole's growth have remained poorly understood. The data from Webb suggests that these jets may play a dual role. Not only do they carry away energy and particles from the accretion disk, but they may also influence the surrounding interstellar medium, shaping the evolution of the host galaxy. The significance of this discovery extends beyond the immediate study of black holes. By observing how supermassive black holes feed, scientists can better understand the feedback mechanisms that regulate galaxy growth. As a black hole accretes matter, it releases enormous amounts of energy in the form of radiation and jets. This energy can heat the surrounding gas, preventing it from cooling and forming new stars. In this way, supermassive black holes act as regulators of star formation, balancing the growth of galaxies with their central engines. The observations from Webb provide direct evidence of this process, showing how the energy released by the black hole's accretion interacts with its environment. This has important implications for our understanding of galaxy evolution, particularly in the early universe when supermassive black holes were thought to form and grow rapidly. By studying these processes in detail, astronomers can refine models of how galaxies and their central black holes co-evolve over cosmic time. Another key aspect of the discovery is the role of the James Webb Space Telescope in overcoming the challenges of observing distant black holes. Traditional telescopes, including those in space, have struggled to capture the fine details of accretion disks due to the vast distances involved and the obscuring effects of interstellar dust. Webb's advanced instruments, however, have allowed scientists to peer deeper into these regions, revealing structures that were previously invisible. The telescope's ability to detect infrared light, which is less affected by dust, has been particularly valuable. This has enabled astronomers to study the accretion disks of black holes in the early universe, where such observations were previously impossible. The data collected from this black hole's feeding process not only confirms existing theories but also opens up new avenues for research, such as the study of how black holes accrete matter at different stages of their growth. The implications of this discovery are far-reaching, both for our understanding of black holes and for the broader field of astrophysics. By observing the detailed structure of an accretion disk, scientists can test the predictions of general relativity in extreme gravitational environments. The behavior of light and matter near a black hole provides a unique laboratory for probing the fundamental laws of physics. Additionally, the study of these phenomena helps us understand the role of supermassive black holes in the cosmic web of galaxies, dark matter, and dark energy. As we continue to refine our observations with instruments like Webb, we are uncovering new layers of complexity in the universe's most powerful objects, bringing us closer to answering some of the biggest questions in science. In conclusion, the James Webb Space Telescope has provided an unprecedented look at a supermassive black hole in the act of feeding, revealing the intricate processes that drive these cosmic giants. By capturing the light emitted from its accretion disk and the surrounding halo of material, scientists have gained invaluable insights into how black holes grow and how their energy influences the galaxies they inhabit. This discovery not only advances our understanding of black holes but also highlights the transformative power of modern astronomy in unraveling the mysteries of the universe. As we continue to explore the cosmos with tools like Webb, we are reminded that the universe is a vast, dynamic place, and its secrets are waiting to be uncovered one observation at a time. The James Webb Space Telescope, launched in 2021, has revolutionized our ability to peer into the cosmos, capturing light from the earliest galaxies and revealing secrets hidden for billions of years. One of its most groundbreaking discoveries came in the form of a supermassive black hole devouring matter in a distant galaxy, an event so luminous and rare that it offered a rare glimpse into the violent life of these cosmic giants. But how did scientists detect this phenomenon? The answer lies in a combination of cutting-edge technology, decades of theoretical groundwork, and the relentless pursuit of understanding the universe's most extreme environments. Let's walk through the process that led to this discovery, step by step. At the heart of this discovery was the James Webb Telescope's ability to observe in the infrared spectrum, a range of light that is invisible to the human eye but crucial for studying distant, dusty regions of space. When light from a galaxy travels across billions of light-years, it is stretched by the expansion of the universe, shifting into longer wavelengths, what astronomers call redshift. The galaxy where this black hole resides is so far away that its light has been redshifted into the infrared, making it detectable only by instruments like Webb's Near-Infrared Camera, NRC, and Mid-Infrared Instrument, MIRI. These instruments are designed to capture faint, diffuse light from ancient galaxies, but they also have the unique capability to resolve the intricate details of structures within those galaxies, including the accretion disks around black holes. Supermassive black holes, which can weigh millions to billions of times the mass of the Sun, are typically shrouded in clouds of gas and dust. When they actively consume matter, whether it's gas, stars, or other debris, they emit intense radiation, creating what's known as an accretion disk. This disk heats up to millions of degrees, emitting light across the electromagnetic spectrum, but much of this light is absorbed or scattered by the surrounding material. The challenge for astronomers is to pierce through this veil and observe the black hole itself. Here's where the James Webb Telescope's advanced optics and sensitivity come into play. Its segmented mirror, composed of 18 hexagonal mirrors, allows it to collect more light than any previous telescope, while its high-resolution imaging capabilities enable it to distinguish fine details in distant objects. By combining these features, scientists could detect the faint, glowing disk of material spiraling into the black hole, even in the presence of obscuring dust. But the journey to this discovery wasn't just about the telescope's technical capabilities. It also required a deep understanding of how black holes behave. For decades, astronomers have studied the relationship between supermassive black holes and their host galaxies, hypothesizing that these monsters grow alongside their galaxies, influencing their evolution. However, direct observations of a black hole in the act of feeding have been extremely rare. The key to this discovery was identifying a galaxy with the right characteristics, one that is actively star-forming, has a massive central black hole, and is positioned in such a way that its light could be observed without being overwhelmed by other cosmic phenomena. The target galaxy, located about 10 billion light-years away, was chosen precisely because it met these criteria. Its distance meant that the light we see today was emitted when the universe was only about 2 billion years old, offering a window into the early stages of black hole growth. Once the telescope was pointed at this galaxy, the next step was to analyze the data. The process of detecting a black hole's accretion disk involves meticulous observation and sophisticated analysis. Scientists used Webb's instruments to capture images and spectra of the galaxy, looking for signs of intense radiation. The accretion disk emits light at specific wavelengths, and by analyzing these emissions, researchers could infer the presence of a black hole. However, the light from the disk is not uniform, it's distorted by the immense gravity of the black hole itself. This distortion creates a phenomenon known as gravitational lensing, where the light bends around the black hole, creating a bright ring of light called an Einstein ring. By studying these distortions, scientists could map the distribution of mass around the black hole and estimate its size. Another critical aspect of the discovery was the use of advanced computational tools. The data collected by Webb is vast and complex, requiring powerful algorithms to process and interpret. Machine learning techniques were employed to sift through the data, identifying patterns that might indicate the presence of a black hole. These algorithms were trained on existing data from other telescopes and simulations, allowing them to recognize the unique signatures of an accretion disk. The process was not instantaneous, it took months of analysis, with teams of scientists working tirelessly to refine their models and cross-check their findings. Every piece of data had to be verified against theoretical predictions, ensuring that the observed phenomena were indeed caused by a supermassive black hole rather than some other cosmic event. The final confirmation came when the team observed a distinct glow around the black hole, consistent with the expected behavior of an accretion disk. The light emitted by the disk was not only intense but also showed variations in brightness, indicating that the material was spiraling inward and colliding with itself, generating heat and radiation. These variations provided further evidence of the black hole's activity, as the accretion process is not steady but rather dynamic, with turbulence and magnetic fields playing a role in the flow of material. The data also revealed the presence of a powerful jet of particles being ejected from the black hole's vicinity, a common feature in active galactic nuclei. These jets, which travel at near-light speeds, are thought to be powered by the black hole's immense gravitational energy and could influence the surrounding galaxy by heating the interstellar medium and regulating star formation. This discovery is significant not only because it provides direct evidence of a supermassive black hole feeding but also because it offers insights into the broader processes that shape galaxies. The relationship between black holes and their host galaxies is a central question in astrophysics, and observing a black hole in action helps refine our understanding of how these systems evolve. The findings suggest that supermassive black holes can grow rapidly in the early universe, possibly through mergers with other black holes or the accretion of vast amounts of gas. This challenges some existing models of black hole growth and highlights the need for further observations to test these hypotheses. The journey from the initial observation to the confirmation of this discovery was a testament to the power of modern astronomy. It combined the precision of advanced instruments like the James Webb telescope with the ingenuity of computational methods and the dedication of a global scientific community. Each step in the process, from selecting the target galaxy to analyzing the data, required careful planning and collaboration. The result is a rare and valuable glimpse into the life of a supermassive black hole, one that continues to shape the universe in ways we are only beginning to understand. As scientists continue to study these cosmic giants, the James Webb telescope will remain a vital tool, unlocking the secrets of the universe one discovery at a time. NASA's James Webb catches a supermassive black hole feeding. This part of our deep dive into NASA's James Webb catches a supermassive black hole feeding focuses on, go deeper into the underlying science/physics/astronomy that makes this significant. Explain why it matters to our understanding of the universe, in accessible plain language. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For viewers who want to go deeper than this summary, the primary source linked in the description lays out the full technical picture. Findings like this rarely stand alone, they get compared against earlier observations to make sure the pattern holds up under scrutiny. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For decades, the cosmos has teased us with its secrets, and among the most enigmatic of these are supermassive black holes. These cosmic behemoths, millions to billions of times more massive than our Sun, lurk at the centers of galaxies, their gravity so intense that not even light can escape their grasp. Yet, for much of the 20th century, they remained elusive, hidden behind the dust and gas of their host galaxies. It wasn't until the advent of powerful telescopes and groundbreaking discoveries that humanity began to unravel their mysteries. Today, the James Webb Space Telescope has captured a moment in time that brings us closer than ever to understanding these cosmic giants, a supermassive black hole in the act of feeding. But how did we get here? How did our understanding of black holes evolve from theoretical whispers to the vivid images we now see? Let's journey through the decades of discovery that made this moment possible. The story begins in the early 20th century, when Albert Einstein's theory of general relativity laid the mathematical foundation for black holes. In 1915, Einstein's equations predicted that massive objects could warp spacetime so drastically that nothing, not even light, could escape their pull. However, these ideas were largely theoretical, confined to the realm of physics. It wasn't until the 1960s that the term black hole itself was coined, thanks to John Wheeler and others who popularized the concept. Yet, even as scientists began to grasp the existence of these objects, there was no way to observe them directly. Black holes, by their very nature, are invisible, their presence inferred only through their gravitational effects on nearby stars and gas. The breakthrough came in the 1960s and 1970s, when astronomers turned their attention to quasars, luminous beacons in the distant universe. These objects, powered by the immense energy released as matter falls into a supermassive black hole, emitted light so bright it outshone entire galaxies. The discovery of quasars suggested that black holes were not just theoretical curiosities but real, active entities at the hearts of distant galaxies. However, the tools to study these phenomena were limited. Ground-based telescopes struggled to peer into the dense clouds of dust and gas that obscured the centers of galaxies, while early space-based observatories lacked the resolution to capture detailed images of these distant objects. The 1990s marked a turning point with the launch of the Hubble Space Telescope. For the first time, astronomers could study the cores of galaxies in unprecedented detail. Hubble's sharp vision allowed them to detect the motion of stars orbiting massive, unseen objects, strong evidence for the existence of supermassive black holes. These observations confirmed that the centers of galaxies harbored these gravitational titans, but they still couldn't see the black holes themselves. The challenge lay in the fact that black holes are surrounded by accretion disks of hot, glowing gas, which emit light as matter spirals inward. Yet, even these glowing disks are faint and obscured by the dusty environments of their host galaxies. To peer through this veil, scientists needed telescopes capable of capturing light in the infrared spectrum, where dust is less opaque. The 2000s brought another leap forward with the launch of X-ray observatories like the Chandra X-ray Observatory. These instruments could detect the high-energy radiation emitted by the superheated gas and accretion disks, providing clues about the behavior of black holes. X-ray data revealed that supermassive black holes often emit powerful jets of particles traveling at near-light speeds, a phenomenon known as relativistic jets. These jets, powered by the black hole's spin and magnetic fields, can extend for thousands of light-years, making them some of the most energetic phenomena in the universe. However, while X-ray telescopes offered valuable insights, they couldn't capture the full picture. The infrared spectrum, which reveals the glow of warm dust and gas, remained a critical frontier for understanding how black holes interact with their surroundings. The 2010s saw the emergence of another revolutionary tool, the Event Horizon Telescope, EHT. This global network of radio telescopes, linked together through a technique called very long baseline interferometry, created a virtual telescope the size of Earth. In 2019, the EHT captured the first-ever image of a black hole's event horizon, the point of no return, located in the galaxy M87. This image, a glowing ring of light surrounding a dark central region, confirmed many theoretical predictions and provided direct visual evidence of a supermassive black hole's existence. Yet, while the EHT revolutionized our understanding of black holes, it couldn't observe the process of feeding in detail. The accretion disks and jets that power these cosmic engines remain shrouded in mystery, particularly in the earliest stages of a black hole's life. Enter the James Webb Space Telescope, launched in 2021. With its advanced infrared capabilities, JWST has opened a new window into the universe, allowing scientists to peer through the dust that has long obscured the centers of galaxies. Unlike previous telescopes, JWST's instruments are designed to detect the faint, redshifted light emitted by distant objects, making it ideal for studying the early universe and the environments around supermassive black holes. The recent discovery of a supermassive black hole feeding, captured by JWST, represents a culmination of decades of technological and scientific progress. This moment is not just a triumph of engineering but a testament to the patience and persistence of astronomers who have spent generations unraveling the secrets of the cosmos. But how did we get here? The journey from theoretical speculation to observational confirmation has been marked by incremental breakthroughs. Each new telescope, from Hubble to Chandra to the EHT, has built upon the discoveries of its predecessors, expanding our ability to probe the universe's most extreme environments. The challenge of observing black holes has always been their invisibility, but by studying the light and energy they emit, scientists have pieced together a picture of these enigmatic objects. Today, JWST's ability to capture the glow of accretion disks and the structure of dusty environments around black holes marks a new era in astronomy. It allows us to witness the very process that fuels these cosmic giants, the relentless dance of matter spiraling into the abyss, releasing energy in the form of light, heat, and powerful jets.
This discovery is more than a milestone in observational astronomy, it is a reminder of how far we've come.
The tools we now use to study black holes are the result of decades of innovation, from the first radio telescopes to the sophisticated instruments aboard JWST. Each generation of scientists has built on the work of those before them, driven by curiosity and the desire to understand the universe. The image of a supermassive black hole feeding is not just a snapshot of a distant galaxy, it is a testament to humanity's ability to peer into the unknown and bring the cosmos into focus. As we continue to explore the universe with instruments like JWST, we are not just uncovering the secrets of black holes, we are expanding the very limits of what we know about the cosmos. The James Webb Space Telescope has captured a rare and dramatic moment in the life of a supermassive black hole, a cosmic behemoth in the act of devouring surrounding material.
This observation, though groundbreaking, is more than just a snapshot of a black hole's feeding frenzy.
It opens a window into one of the most enduring mysteries in astrophysics: how these colossal entities form, grow, and shape the galaxies they inhabit. While the telescope's ability to peer into the distant universe has revealed unprecedented details about this event, it also highlights gaps in our understanding.
Scientists are left with a series of profound questions, each more tantalizing than the last. How did this black hole, and others like it, reach such monstrous sizes so quickly? What forces drive their relentless growth? And what role do these hungry giants play in the evolution of the cosmos? These questions are not just academic, they are central to unraveling the fundamental processes that govern the universe. The James Webb's observation of this black hole is a critical piece of the puzzle, but it also underscores the vastness of the unknown.
For every answer it provides, it raises new mysteries, inviting scientists to dig deeper into the cosmic dance between black holes and their environments. Let's explore what this discovery tells us, and what it still leaves unanswered. At the heart of this observation is a supermassive black hole, a gravitational monster with a mass millions or even billions of times that of our Sun. These objects are found at the centers of most galaxies, including our own Milky Way.
But how did they get so big so fast?
Theories suggest that supermassive black holes form through a combination of processes, including the collapse of massive stars, mergers with other black holes, or the direct collapse of gas clouds in the early universe.
However, the James Webb's recent findings complicate this picture.
The black hole in question is actively accreting material, a process in which it pulls in gas, dust, and even stars from its surroundings. This accretion releases immense energy, creating the luminous disks and jets that astronomers can observe. Yet, the rate at which this black hole is growing challenges existing models.
If it is consuming material at such a high rate, how does it avoid the physical limits that typically constrain accretion?
These limits, known as the Eddington limit, suggest that a black hole cannot grow faster than a certain rate without destabilizing its accretion disk. But the James Webb's data implies that this black hole is defying such constraints, hinting at either an incomplete understanding of the physics at play or the presence of additional factors that allow for rapid growth. This discrepancy is a key point of debate among scientists. Some argue that the black hole's environment, perhaps a dense cluster of gas or an unusually massive accretion disk, could be enabling this accelerated growth. Others propose that the black hole may be interacting with nearby objects, such as other black holes or stars, in ways that haven't been fully accounted for in current models. These possibilities underscore the complexity of black hole formation and evolution, and the need for further observations to test them.
One of the most intriguing aspects of this discovery is its implications for the early universe.
Supermassive black holes are thought to have formed within the first few 100 million years after the Big Bang, yet their rapid growth remains a puzzle. The James Webb's observation of this black hole, which is located in a distant galaxy, suggests that such extreme accretion events may have been more common in the early cosmos than previously believed. This raises the question, how did these black holes reach their massive sizes so quickly? One hypothesis is that they formed from the direct collapse of massive gas clouds, bypassing the slower processes of stellar evolution. However, this theory is still speculative, and the conditions required for such a collapse are not fully understood. Another possibility is that these black holes grew through frequent mergers with other black holes, a process that could accelerate their mass accumulation. Yet, the James Webb's data suggests that this black hole is not just growing through mergers, it is consuming vast amounts of surrounding material in a way that defies conventional models. This has led some scientists to propose that the black hole may be in a unique phase of its evolution, one that is not yet fully captured by existing theories. Whether this is a rare exception or a common phenomenon remains unclear, and further observations are needed to determine its significance.
The role of dark matter in the growth of supermassive black holes is another area of active debate.
While dark matter itself does not interact with electromagnetic forces, its gravitational influence is thought to play a critical role in shaping the structure of galaxies.
Some researchers suggest that dark matter could provide the necessary scaffolding for gas to accumulate in the vicinity of a black hole, fueling its growth. However, the exact mechanism by which dark matter influences black hole accretion is still unclear.
The James Webb's observation of this black hole offers a potential clue. If the black hole's environment is unusually dense with gas or dark matter, it could explain the rapid accretion rates observed.
Yet, without direct measurements of dark matter distribution in such regions, these ideas remain speculative.
The challenge lies in distinguishing between the effects of dark matter and other factors, such as the presence of nearby stars or the dynamics of the host galaxy. This highlights the need for complementary observations, such as those from radio telescopes or gravitational wave detectors, to piece together the full picture of how black holes interact with their environments.
Another unresolved question is the feedback mechanisms between supermassive black holes and their host galaxies.
These mechanisms, often referred to as feedback loops, are thought to regulate galaxy growth by influencing the availability of gas for star formation. When a black hole accretes material, it releases energy in the form of radiation and powerful jets, which can heat or expel gas from the galaxy, thereby suppressing star formation.
However, the James Webb's observation of this black hole suggests that the relationship between the black hole and its host galaxy may be more complex than previously thought.
The data indicates that the black hole's activity is not only consuming material but also potentially triggering new processes in its environment.
For example, the intense radiation from the accretion disk could ionize surrounding gas, altering its chemical composition and affecting the formation of new stars.
Alternatively, the jets emitted by the black hole might be interacting with the galaxy's interstellar medium in ways that have not yet been fully modeled. These interactions could have far-reaching consequences for the galaxy's evolution, yet the precise mechanisms remain a subject of debate. Understanding these feedback loops is crucial for determining how supermassive black holes influence the structure and dynamics of their host galaxies, but the James Webb's findings suggest that the relationship is far more intricate than previously assumed. The James Webb's ability to observe this black hole in such detail is a testament to the power of modern astronomy, but it also highlights the limitations of current observational techniques. While the telescope has provided unprecedented insights into the black hole's feeding behavior, it cannot capture every aspect of the process. For instance, the observation is limited to the visible and infrared wavelengths, which means that some key details, such as the precise distribution of gas or the presence of magnetic fields, remain elusive.
Additionally, the black hole's environment is likely to be dynamic, with accretion rates and jet activity varying over time.
Capturing these changes requires long-term monitoring, which is challenging given the vast distances involved.
The James Webb's data, therefore, represents a single snapshot in a much larger, ongoing process. This underscores the importance of continued observations and the need for a multi-wavelength approach to studying black holes. By combining data from different telescopes and instruments, scientists can build a more comprehensive picture of these cosmic phenomena. Despite the challenges, the James Webb's observation of this black hole is a milestone in our quest to understand the universe. It has provided valuable insights into the nature of supermassive black holes and their role in cosmic evolution, but it has also revealed the depth of the mysteries that remain. The black hole's rapid growth, the potential influence of dark matter, the complexities of feedback mechanisms, and the limitations of current observations all point to a field of study that is both rich and full of unanswered questions. These mysteries are not just scientific puzzles, they are fundamental to our understanding of how the universe operates.
As scientists continue to refine their models and gather more data, they will undoubtedly uncover new insights.
But for now, the James Webb's observation serves as a reminder that even with the most advanced technology, the cosmos still holds secrets waiting to be discovered.
The journey to unravel these mysteries is just beginning, and each new discovery brings us closer to understanding the profound forces that shape our universe. As the James Webb Space Telescope continues to unveil the secrets of the cosmos, its groundbreaking observation of a supermassive black hole in the act of feeding has opened a new chapter in astrophysical research.
This moment, captured in the infrared spectrum, is not just a snapshot of a distant celestial event, it's a beacon for future exploration. What lies ahead is a tapestry of upcoming missions, instruments, and observations that promise to deepen our understanding of these enigmatic cosmic entities. From the next generation of space telescopes to ground-based observatories and even the detection of gravitational waves, the scientific community is poised to build on this discovery in ways that could redefine our knowledge of black holes and their role in the universe. The first step in this journey is the continued operation of the James Webb Space Telescope itself. While its current observation is a milestone, the telescope's instruments are designed for long-term, high-resolution studies.
Future observations using JWST's near-infrared camera, NIRCam, and mid-infrared instrument, MIRI, could provide more detailed data on the black hole's accretion disk, the surrounding gas, and the dynamics of the galaxy it inhabits. These follow-up studies might reveal how the black hole's feeding activity influences its host galaxy, a critical piece of the puzzle in understanding the coevolution of supermassive black holes and their galactic environments.
By comparing these data with previous observations, scientists can track changes over time, offering insights into the black hole's growth and the processes that fuel its immense appetite.
Beyond JWST, the Nancy Grace Roman Space Telescope, set to launch in the mid-2020s, will play a pivotal role in extending this research. Designed to survey vast swaths of the sky with unprecedented precision, the Roman telescope will focus on dark energy and exoplanets, but its capabilities also make it an ideal tool for studying black holes. Its wide-field imaging could help identify more supermassive black holes in the early universe, providing a broader context for the one observed by JW. Additionally, Roman's ability to detect subtle gravitational lensing effects, where the gravity of a massive object bends light from distant sources, could reveal hidden structures around black holes, such as the elusive event horizon. These observations might also shed light on the distribution of dark matter in the vicinity of these cosmic giants, further bridging the gap between theoretical models and empirical data. Ground-based observatories are equally vital in this quest. The Extremely Large Telescope, ELT, currently under construction in the Atacama Desert of Chile, will soon boast a 39-meter mirror capable of capturing light from the earliest galaxies and black holes. Once operational in the 2020s, the ELT will complement JWST's findings by providing higher-resolution images and spectra. Its adaptive optics technology will allow astronomers to peer through the turbulence of Earth's atmosphere, revealing details that even space-based telescopes cannot achieve. For instance, the ELT could map the distribution of gas and stars around the black hole in exquisite detail, helping to determine how efficiently the black hole is accreting matter. These data might also uncover the presence of previously undetected stellar remnants or gas clouds that contribute to the black hole's growth, offering a more complete picture of its feeding mechanisms. Another key player in this future exploration is the upcoming Lynx X-ray Observatory, a proposed next-generation X-ray telescope that could revolutionize our understanding of black hole activity. X-ray observations are crucial for studying the extreme environments around black holes, where temperatures can reach millions of degrees. The Lynx, if approved, would have a much larger mirror than current X-ray telescopes, enabling it to detect fainter sources and resolve finer details. By focusing on the high-energy emissions from the black hole's accretion disk and jets, Lynx could provide direct evidence of the physical processes driving the black hole's feeding. For example, it might measure the spin rate of the black hole, a factor that influences how efficiently it converts mass into energy. Such data would not only validate existing theories but also challenge them, potentially leading to new models of black hole behavior. The study of black holes is also deeply intertwined with the detection of gravitational waves, ripples in spacetime caused by massive cosmic events. Instruments like the Laser Interferometer Space Antenna, LISA, scheduled for launch in the 2030s, will open a new window into the universe by detecting these waves. While LISA is primarily designed to observe mergers of supermassive black holes, its sensitivity could also capture the subtle gravitational disturbances caused by the accretion of matter. These signals, though faint, might provide indirect evidence of the black hole's feeding activity, complementing the electromagnetic observations from JWST and other telescopes. The combination of gravitational wave data with traditional astronomical observations could reveal the full spectrum of a black hole's interactions, from the slow, steady accretion of gas to the violent mergers that define its life cycle.
In addition to these specialized instruments, the collaborative efforts of international observatories will play a critical role in advancing this research. Projects like the Square Kilometre Array, SKA, a next-generation radio telescope network, will contribute by mapping the magnetic fields and ionized gas surrounding black holes. These observations could help scientists understand how magnetic forces influence the flow of material into the black hole, a process that remains one of the greatest mysteries in astrophysics. Similarly, the upcoming Athena X-ray Observatory, part of the European Space Agency's (ESA) plans, will provide high-resolution X-ray data that could refine our understanding of the black hole's environment. By combining data from these diverse instruments, researchers can piece together a multidimensional view of the black hole's activity, from the cold, distant gas clouds to the superheated plasma in its immediate vicinity. The future of black hole research also hinges on the development of new analytical techniques and computational models. As the volume of data from missions like JWST and the ELT grows, machine learning and artificial intelligence will become essential tools for processing and interpreting this information. These technologies can help identify patterns in the data that might be missed by traditional methods, such as subtle variations in the black hole's accretion disk or unexpected interactions between the black hole and its host galaxy. Additionally, simulations of black hole behavior will become increasingly sophisticated, allowing scientists to test hypotheses against real-world observations. For example, models predicting how a black hole's feeding activity affects its surroundings could be refined using data from future missions, leading to more accurate predictions of black hole behavior in different cosmic environments. One of the most exciting possibilities is the potential for this research to challenge existing theories about black holes. While the current understanding of supermassive black holes is based on decades of observations, the data from JWST and future missions could reveal anomalies or unexpected behaviors that require new explanations. For instance, if the black hole's feeding activity is found to be more efficient or less efficient than predicted, it could indicate gaps in our knowledge of how black holes interact with their surroundings. Similarly, the discovery of new phenomena, such as previously undetected emissions or unusual accretion patterns, might lead to the development of entirely new theories about black hole physics. These challenges are not setbacks but opportunities to push the boundaries of scientific inquiry, ensuring that our understanding of these cosmic giants continues to evolve. As we look to the future, the study of supermassive black holes is not just about understanding these objects in isolation. It is about unraveling their role in the broader context of the universe. Black holes are not merely cosmic vacuums, they are dynamic entities that shape the evolution of galaxies, regulate star formation, and influence the distribution of matter on a cosmic scale. The observations from JWST and the upcoming missions will help clarify how these processes unfold, offering insights into the interconnected web of cosmic phenomena. For example, understanding how a black hole's feeding activity affects its host galaxy could provide clues about the formation of large-scale structures in the universe, from galaxy clusters to the cosmic web itself. These connections underscore the importance of continued exploration, as each new observation brings us closer to a unified understanding of the cosmos. In conclusion, the James Webb Space Telescope's observation of a supermassive black hole feeding is more than a scientific milestone, it is a catalyst for a new era of discovery. The future missions and instruments described here represent the next steps in this journey, each contributing a unique piece to the puzzle of black hole physics. From the vast surveys of the Roman Space Telescope to the high-resolution imaging of the ELT, from the X-ray insights of Lynx to the gravitational wave detections of LISA, the scientific community is equipped with an array of tools to explore the mysteries of these cosmic giants. As these technologies come online, they will not only build on the current findings but also challenge existing paradigms, ensuring that our quest to understand the universe remains as dynamic and exciting as the cosmos itself. NASA's James Webb catches a supermassive black hole feeding. This part of our deep dive into NASA's James Webb catches a supermassive black hole feeding focuses on, briefly recap the 2 or 3 biggest takeaways from this deep dive in a satisfying way, then invite the viewer to subscribe to FactVerse for daily space deep dives and to comment their own theory or question. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own.
It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For viewers who want to go deeper than this summary, the primary source linked in the description lays out the full technical picture. Findings like this rarely stand alone, they get compared against earlier observations to make sure the pattern holds up under scrutiny. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable.